Good morning, everyone. I'm Guan-Ting from National Jiao University in Taiwan. I will talk about an interesting topic and contact lens sensor system with a micro-capacitor for wireless intraocular pressure monitoring. Here is my outline. I will introduce the motivation and then show how I designed and fabricated of IOP microcapacitor sensors. Finally, I will present the experiment result and the conclusion. Left picture is a simple eyes model, and close up on right. Normally, the aqueous fluid flow into the front chamber and leave the ice in the ice drainage system. The other two situations, here is blocked, so aqueous fluid cannot leave the ice, so the intraocular pressure will increase. So glaucoma caused mainly by increased intraocular, you can call that IOP, can damage the optic nerve and lead to blindness. Glaucoma cannot be cured, but we can only prevent the disease from getting worse by medicine or surgery to reduce the IOP. So, monitoring patients' IOP regularly and treating by medicine timely can prevent them from blindness. The traditional tonometer, like government application tonometer, can provide accurate and reliable IOP measurement, but it cannot provide real-time and long-term IOP measurement. It's also not portable and wearable because it's cumbersome and cumbersome volume. The other type tonometer, like invasive IOP tonometer, it can provide real-time and long-term IOP measurement, but it needs to be surgical implanted into the eyes and cannot be accepted by most health people. Left picture is our sensor system design. The sensor and the antenna is ring shape, will not block the subject vision, and the antenna and sensor will implement by using MEMS fabrication method. The bottom picture is our system overview. We use 5.8 GHz and 2.4 GHz for wireless powering and data transmission. So it can provide this system can provide real-time and long-term IOP measurement. So I talk about design of my sensors. Left picture is my sensors design. Its inner and outer diameter are 9 mm and 11 mm. The red and the blue part of the sensor system are the top and the bottom electrodes of capacitor sensors with 80 cogs respectively. And the purple parts show the top and the bottom electrode overlap area. Each area about 40 micrometer by 100 micrometer. The distance between the top and the bottom electrodes is 10 micrometer. And the bottom figure show that how the sensor work on the cornea. when the IOP increases, the contact lens will move on the surface of the cornea, and then it bends and follow the corneal deformation. When the IOP increase, the distance between the top and the bottom electrodes distance will decrease. Then my capacitor value will increase. Now I talking about my fabrication process. Step 1, we sputter the copper for a sacrificial layer and deposits parency 1 micrometer and define bottom electrode, and then we deposit parency 5 micrometer. Parency as the metal insulating layer, and the parency and the gold are biocompatible material. Step 2, we dry etching, define the shape of the fin, then spin coating the photoresist as a sacrificial layer between top and bottom electrode. Step 3, we deposit parency 1 micrometer and define the top electrode, and then we deposit parency 5 micrometer and the parency as the metal insulating layer. Step 4, we dry etch we dry etching and define the sensor shape of the sensor, then open the pad to provide a connection with our outside pad. Step 5, we release the device and finish the process. Left picture is our device, and before integrating soft contact lens. The right picture is our device is embedding in the soft contact lens. Zero swelling ratio HEMA was chosen as a material of soft contact lens. The advantage of HEMA is gas permeable and hydrophilic and antibacterial. It's also soft and flexible so that it can deformation with the cornea. I will show the experiment and result. I will introduce the experiment environment setup. The bottom picture is the human eyes-like balloon. It was designed. It has the similar shape and size with human cornea. First, we put the device on the human eyes-like balloon. Then surgery pump connects to the T-pipe, which can bypass the water flow to the eyes-like balloon and the pressure transducer. The pressure transducer can detect the water pressure. Inside the human eyes-like balloon, and read out the pressure value. Then the sensor was connected to impedance analyzer, and the capacitance value was measured. And this is my experiment result. Next step is we inject the water to the human eyes-like balloon. The right step, we draw the water from the human eyes-like balloon. Each step will inject or draw 50 microliter water. This figure shows the sensor has good reproducibility and relativity. This figure shows that our sensor has good linearity and it's sensitive about 0.43 picofarad per mmHg. Finally, we talk about conclusion. A micro-capacitor for non-invasive IOP measurement was successfully implemented and tested in this study. The sensitivity of the proposed sensor is about 0.43 picofarad per mmHg, and this is very useful for IOP measurement. The proposed micro-capacitor can also provide good stability, reproducibility, and feasibility in the experiment. In future work, the fabrication process will be optimized for stable micro-capacitor production. We will integrate with the RFIC and test on enucleative partial ice. And thanks for your attention.